All right, so into this week's class, in this week's unit, we're going to be talking about domain, intercepts, and asymptotes for graphs of a function. Now, even though all of these characteristics of a function pertain to a graph, we're not actually going to be looking at any graphs. Instead, what we're wanting to do here is get the information, the domain, the x and y intercepts, and the horizontal or vertical asymptotes from the functions without having a graph to look at. The goal here is to help with section 3.3 in our parent class this week when we're talking about the graphing strategy. In that section, in the parent class, we're going to be using some algebraic techniques that you would have learned already, as well as some calculus techniques that we are currently learning to extract a whole lot of information out of a function so that you can use that information to sketch a graph of it by hand. Now, this is the support class, and so we're not going to talk about the calculus stuff here. We're going to talk about the prerequisite algebra type stuff that you should already know, but might need practice on. So for each of the functions that we're going to look at, we're going to look at 4 today. We want to find those 3 categories of things: domain, x and y intercepts, horizontal and vertical asymptotes, assuming they exist. Now, lots of functions don't have any kind of asymptote. Some functions don't have any x-intercepts at all or y-intercepts. So these may not all exist for every function that we look at, but we're going to try and find all of the things that do exist. So the function that we're starting with is y equals 4x to the 4th plus 20x cubed minus 200x squared. This is a polynomial. One thing that we know about all polynomials is that the domain for a polynomial is all real numbers, which we can denote with this interval from negative infinity to infinity. That is an automatic for any polynomial because I can plug any real number I want in for x and I always get some kind of an output from it. How do we find x and y intercepts? Well, remember, if I have the graph of some curve and there's a y-intercept somewhere for that curve and an x-intercept for that curve, the place where the curve passes through the y-axis would have to be where the x-coordinate of the point there is equal to 0, right? Because that's 0 on the x-axis. Anything on the y-axis has an x-coordinate of 0. Similarly, if I'm looking for an x-intercept, I would be setting y equal to 0. Okay, so that's the key to finding these things. This is the function I'm given. If I want to find my x-intercept, I would set y equal to 0. So let's try that. If I set y equal to 0, then 0 is equal to this polynomial. 4x to the 4th plus 20x cubed minus 200x squared. And now it's solving a polynomial equation. Okay, so as you know, the best way to solve a polynomial equation is to factor the polynomial if that's a possibility and then solve using the zero product property. So I see that I can pull a common factor of 4x squared out of everything here, which would leave me with just an x squared there plus 5x there minus 50 there. This quadratic polynomial in parentheses can be factored further. It's the same thing as x plus 10 times x minus 5. And if that's equal to 0, then each of these factors in that product could be set equal to 0 separately to find all possible values of x that would make this true. By this point, though, we should be able to do that without having to actually write out 4x squared equals 0, x plus 10 equals 0, x minus 5 equals 0, and then solving those with algebra. You should be able to look at that and see that the solutions are 0, negative 10, positive 5. Should be that fast. Okay? Each of those x values gives me an x-intercept. But notice that when I write my x-intercepts, I'm not just writing x equals 0, x equals negative 10, x equals 5. I have to specifically write them as points. So 0, 0, negative 10, 0, 5, 0, Notice in all three of them, the y-coordinate is 0 because that's the defining characteristic of an x-intercept. It's where your y-coordinate is 0. Another thing that's worth mentioning here, a couple of things. To find the y-intercept, it's generally easier to do that than to find the x-intercept because you're plugging 0 in for x. And I can see just by looking at this, if I plug a 0 in for x, all of that's going to go to 0 immediately. So my y-intercept is 0, 0. Notice how we have a common x-intercept and y-intercept at the origin, 0, 0. That is the only point in the entire plane that can be both an x and a y-intercept because it's the only point that the x and y axes have in common. That doesn't mean that it's always going to be one of your intercepts, but it is possible that it could show up as both. In fact, if it shows up as one, it has to show up as the other because it's on both axes, okay? Another thing worth mentioning, functions can have several x-intercepts, but at most they can only have one y-intercept. And there's a very clear reason for why that's true. If you remember from algebra, we learned that functions, their graphs specifically, have to pass something called the vertical line test. So if a function has more than one y-intercept, say 2, let's suppose that this function has a y-intercept here and another one here, then that would mean that it fails the vertical line test because I could put a vertical line through that curve and I would hit it in more than one spot. If a graph fails the vertical line test, that means that you did not have a function in the first place. We are only dealing with functions in this assignment, so there will only ever be one y-intercept, even if there are multiple x-intercepts. Okay? Finally, asymptotes. Polynomials have neither type of asymptote. In their end behavior, meaning as x goes towards infinity or negative infinity, the graphs of polynomials always go to either positive or negative infinity. They never level out and start approaching some finite value. There's also no discontinuities in a polynomial because we need those for vertical asymptotes. So there are no asymptotes at all. Okay? So here is all the information that was asked for this polynomial. Let's move on to a harder function. Polynomials are really the easiest types of functions to do a problem like this with because they have the most convenient characteristics. But let's try a rational function. Let's say y equals 6 times x minus 1 squared over x squared plus 8x minus 9. Okay? So again, we want to do all the same stuff. We want to find the domain. We want to find the x-intercepts, y-intercepts, asymptotes if there are any. And so to start with the domain, we know that with rational functions, we start by looking for what would make the denominator equal to 0. And in this case, it would help to factor that denominator first before we start doing that. Okay, so this denominator factors pretty nicely, x plus 9 times x minus 1. And I can see from that if my x is either equal to negative 9 or positive 1, then I'm going to have discontinuities. So my domain cannot include either of those values. So what we're seeing here is that x is not equal to negative 9 or 1. Okay. So my domain, I would typically write in interval notation. So negative infinity to negative 9, union negative 9 to 1, union 1 to infinity. Remember that these have to be open intervals. If you use square brackets, you're implying that whatever end point you put that square bracket on is part of this domain, but that would be including either a negative 9 or a 1 when we're saying that we don't want to include those. All right. Now, from these discontinuities, we can get vertical asymptotes. So I'm going to do the asymptotes next. Instead of the x and y intercepts, we'll do those last. But it's not just an automatic, right? It's not just automatically that I have vertical asymptotes in both of these locations. Because if a factor cancels out, like this x minus 1 here, then what I get is 6 times x minus 1 over x plus 9. And the only thing left in the denominator is that x plus 9. When this x minus 1 cancels out, what that actually implies is that at x equals 1, whatever point that would correspond to, my graph will have a hole in it, not a vertical asymptote. The vertical asymptotes only come from those zeros of my denominator that appear after everything has been canceled out. So x equals -9 is the only vertical asymptote. Okay? What about horizontal asymptotes? How do we find those? Well, remember, a rational function, we've talked about this in a previous section in the parent class. There's only two cases where you get horizontal asymptotes from a rational function. And that is if the degree of the polynomial in your numerator and denominator is the same, then you will get some finite non-zero horizontal asymptote. If the degree of the numerator is smaller than the degree of the denominator, what that tells me is that the denominator gets bigger faster than the numerator does. And a large denominator compared to a small numerator gives me a small number, something close to 0. So in the limiting case, that would go to 0. That tells me if the degree of my numerator is smaller than the degree of my denominator, I'm going to have another horizontal asymptote, but it's going to be at x equals or y equals 0. If the degree of my numerator is larger than the degree of my denominator, then there is no horizontal asymptote at all. So in this case, the degrees of these polynomials match, because if I were to square x minus 1, then I would get an x squared term in there times 6. I'm going to have a 6x squared. That's going to be the highest degree term in my numerator. My denominator is also a quadratic, so I'm going to have a quadratic over a quadratic. How do we then get the horizontal asymptote from that? So if I'll go ahead and expand that out. My numerator is going to turn into 6x squared minus 12x plus 6 if everything gets multiplied out. And then x squared plus 8x minus 9. So again, see, the degree is the same. They're both second degree polynomials. To find a horizontal asymptote in this case where the degrees match, we take the leading coefficient of each term, there's a 1 there, and we just divide them. 6 divided by 1 gives me y equals 6 for my horizontal asymptote. Okay, we framed this in terms of limits in the parent class, but you can technically understand this without needing to know the more formal approach with limits if you just kind of remember that trick there. What about x and y intercepts? Well, again, we get x intercepts from setting y equal to 0 and solving for x. So if I set 0 equal to 6 times x minus 1 squared over x squared plus 8x minus 9, and if I try to solve this, then I could multiply both sides by this denominator, which would give me 6 times x minus 1 squared equals 0, and then x would have to equal 1 in that case. So if x equals 1, my numerator will come out to 0. The problem with that, though, is that my denominator would also be 0. So as we already said, x equals 1 is not even in the domain of this function. So even though it would give me a 0 in the numerator, which is what I'm looking for here, it's an unusable value, and it's the only value that would have given me that 0 in the numerator that I'm looking for. The consequence here is that there is no x-intercepts. No x-intercepts. This graph, whatever it looks like, will never cross the x-axis. What about a y-intercept? Well, y-intercept, we plug 0 in for x instead. So that becomes 6 times 0 minus 1 squared over 0 squared plus 8 times 0 minus 9, right? And in practice, you probably don't need to write all of that. You can do this mentally really easily. But I get negative 1 squared, which is 1 times 6. That's 6 over negative 9, or negative 2/3. That gives me the y-coordinate of my y-intercept. So my y-intercept is 0. That was the x value. Negative 2/3. That's the y value. And here's all the information that we needed, okay? Let's try a couple more. These last two examples that I'm going to do are going to involve either the exponential function, e to the x, or the natural log function. And for those, each of those has one of the types of asymptotes that we're talking about. And we're going to talk about a property of those things. So first of all, before I get into the example, suppose we have a function of this form, f of x equals p of x times e to the x, where p of x is some polynomial. Okay? We'll return to the polynomial part in a second, but let's look at the e to the x function, okay? Remember, e to the x has this shape to it. It's exponential, and it shoots off to infinity really fast over here, but going the other direction, it shrinks down towards 0, but never reaches it. So y equals 0 is a horizontal asymptote for the exponential function. Now, if I take my e to the x function and I multiply it by a polynomial, polynomials can do different things. They can, give me, they can go towards infinity or negative infinity in their end behavior. Specifically, though, they don't have horizontal asymptotes. So what can I say about a horizontal asymptote when my function looks like this? Well, the key thing here is that the exponential function both grows and shrinks way, way faster than any polynomial will. And we can't show that really formally here. We need something called L'Hopital's rule to prove that, which is something we would cover in a full calculus course, but not really in this one. So the key thing to remember here is that as x gets bigger, both e to the x and this polynomial, assuming it has a positive leading coefficient, wants to get really, really big. If it has a negative leading coefficient, it's going towards negative infinity. But I'm not as concerned about what's going on over here as I am what's going on over here. So if you have a polynomial, as x gets smaller, then the polynomial is going to be either approaching positive infinity or negative infinity, while e to the x is trying to go to 0. It's not going to either of those. And so there's like a competition that's happening. Let's just suppose for a second that p of x is going to positive infinity as x gets smaller and smaller, like as x approaches negative infinity. Then there's a competition happening here. You're getting a very, very large number, meaning, approaching infinity, times a very, very small number approaching 0. So which of these is going to win? Which of these is going to determine what happens with this product? And the key thing here is when you're multiplying by an exponential function, the exponential function always wins, assuming that's a polynomial. So what that means is it doesn't matter if the p of x is going to infinity or negative infinity. The fact that I'm multiplying it to an e to the x means that exponential function is going to drag it down to the x-axis anyways. So this will still have a horizontal asymptote of 0, but only as the function goes to the left. What if instead, so this is like y equals e to the x, what if I have something like this, a polynomial over e to the x? Well, that's the same thing as p of x times e to the negative x. And we saw in the first week of class that if you put a negative up here, you get a reflection of this graph across the y-axis, right? So that graph would look like this. Y equals e to the negative x. That also has a horizontal asymptote, but this time as x approaches infinity instead of negative infinity. So we still get the same horizontal asymptote here, but the graph will approach it going the other direction, okay? What about if we have a function like this, h of x equals some polynomial p of x times the natural log of x? Well, remember the graph of the natural log function looks like this. Remember, it's a reflection of the e to the x function across the line y equals x. So it has similar behavior, but it's reflected. So what happens now is this horizontal asymptote for my e to the x function has become a vertical asymptote for my natural log function. But in essence, the same kind of thing happens. If I multiply some polynomial by the natural log function, the natural log function is wanting to drag this polynomial down towards negative infinity as we get over here, right? Assuming p of x has a positive leading coefficient. So in that sense, the natural log function is going to win by keeping this vertical asymptote as it is. So let's start looking at some examples now. Number 3. We're doing the same stuff as before. Finding domain, asymptotes, intercepts. So I'm going to set y equal to x squared minus 100 times e to the x. I'm going to start by finding the domain for this function. I have a polynomial times an exponential function, both of which have a domain of all real numbers, so their product automatically has the same domain. The domain is, again, all real numbers. Okay? What about intercepts? Let's do those next. If I want to find the x-intercepts, then I'd be setting y equal to 0. So 0 equals x squared minus 100, which factors to x plus 10 times x minus 10 times e to the x. And I'm looking for the solutions to this. Well, I use my zero product property, and I can see that plus or minus 10 are solutions to this from these first two factors. If you set e to the x equal to 0, you get no solution because e to the x can only be positive. So plus or minus 10 are the only solutions I'm going to get. Okay, those give me my x-intercepts. So you can do this. You can actually write plus or minus 10, 0. What that means is that we're talking about 2 points, 10, 0 and negative 10, 0, but this is an acceptable kind of shorthand for that. For my y-intercept, I plug 0 in for x. So y is equal to 0 squared minus 100 times e to the 0. Well, this would be negative 100, and e to the 0 is equal to 1, so negative 100 times 1 is just negative 100. That gives me the one y-intercept for this function. 0 is my x-coordinate, negative 100 would be my y-coordinate. Okay, next up, horizontal asymptotes. Well, we kind of discussed what to do in a case like this, because what we have is a polynomial times e to the x. And we said that if f of x is equal to some polynomial times e to the x, there will be a horizontal asymptote. It's not going to affect the graph as x approaches infinity, but it will affect the graph as x approaches negative infinity. So in particular, it will still have the same horizontal asymptote that e to the x has, because e to the x will always overpower any polynomial. So if e to the x has a horizontal asymptote at y equals 0, then so does this function at y equals 0. Now this is not a typical notation, but I tend to do this. What this is an arrow pointing to the left, and it's indicating that this horizontal asymptote only applies to the part of the function that's going towards the left and not the part that's going towards the right. You don't have to include that, but that's helpful when you actually use this information to graph functions in the parent class. This thing has no vertical asymptotes. And why is that? Well, remember, this function is defined everywhere, so there's no discontinuities where we would normally see a vertical asymptote. And that gets me all of that information. Let's do one more problem, and then we're good to wrap this up, I think. Y equals 2x plus 3 times the natural log of x. I want to try and find all this information again, starting with the domain. So this function is equal to a linear function, which has a domain of all real numbers, times a natural log function, which has a domain of only the positive real numbers. That implies that the domain here is also only the positive real numbers, the interval from 0 to infinity. What about x and y-intercepts? Let's look at those next. So for finding an x-intercept, I would be setting y equal to 0, 2x plus 3 times the natural log of x. And that means either 2x plus 3 is equal to 0 or the natural log of x is equal to 0. If I set 2x plus 3 equal to 0 and solve, I get x equals negative 3/2. And if I set natural log of x equal to 0, we know that the natural log of x is equal to 0 when x is equal to 1. However, these are not both usable values because, again, the domain of our function includes only the positive real numbers. So even though -3/2 would cause this term to equal 0, this term, this factor of the natural log function is not defined for that. So I can't use that, okay? That tells me that my x-intercept only is only this one right here. It's when x is equal to 1, and then y, of course, would be equal to 0. Okay, y-intercepts. This function has no y-intercepts. Why is that? Well, remember, the way that you find a y-intercept is you plug 0 in for x. But 0 is not in the domain of this function, so we're not allowed to do that. The function would be undefined. So there's no possibility of getting a y-intercept. Now let's look at asymptotes. Okay, we know that the natural log function, which we have a graph of here, has a vertical asymptote but no horizontal asymptote. So there is no horizontal asymptote for this function, but the vertical asymptote does exist, and like we said over here, or kind of in our discussion before we did these two examples, if you multiply a polynomial times a natural log function, polynomials don't naturally have, what's the word I'm looking for? I lost my train of thought for a second there. They don't have vertical asymptotes at all. So anywhere where you plug in a specific x value, you're going to get a finite y value. Whereas for the natural log function, this is approaching -infinity down here. Okay. Now the one thing to keep in mind is that if you multiply by something that is negative, it can flip this graph around. So even though we do have a vertical asymptote, we don't know whether it's going down or up, but we do know that it's at x equals 0. So my vertical asymptote is at x equals 0. Now I said we don't know whether the graph of our function down here is going to be approaching x equals 0 this way or that way, but we can determine that by thinking a little bit more about this function specifically. So if you plug in a value of x that's very close to 0, like x equals, 0.01 or 0.0001 or 0.000001, right? This term is going to shrink towards 0, but then we're going to add a 3 to it. So this function here is going to be approaching +3, while the natural log function is approaching -infinity. So it's a positive number times a negative number, which is negative, which means our function should still be approaching -infinity. So for my vertical asymptote, if I want to indicate the direction that my function approaches that, I can use that. Similar to the arrow that we used in the previous example. Okay, that's going to be it for the support course. This should help us with the graphing stuff that we do in the parent course this week.